and the geometrical transformations that we have to perform in order to get from joint j minus 1 or coordinate frame j minus 1 to coordinate frame j are the following. These are numbered in these gray circles in here. So, in order to get from j minus 1 to j, first we are going to make a turn of theta j angle around the zj minus 1 axis. Okay, so this would change the axis xj minus 1 and yj minus 1, but this would leave the z-axis equal. This leaves the z-axis unchanged. Okay, so the second operation that is going to be performed in order to reach from j minus 1 to j is a linear displacement of dj, of a parameter called dj, okay, or a variable that displaces the origin of j minus 1 along the z-axis, okay, the z-axis that was resulting from the previous operation that was in fact the original z-axis of the j minus 1 joint. Okay, so after that we will have something like a coordinate frame in here. Okay, the z-axis remains unchanged. It is still the axis of rotation, and then at this moment we should have something like, okay, let me be more precise. We should have something like one direction of x here and one direction of y here. Okay, so the next motion that we are going to do is displace the origin of the resulting coordinate frame a distance called aj, okay, along the x-axis, which takes us to this point, okay, this new origin, right? And then from that moment we will have still the x-axis in the same direction that we had it in the previous move, and the next move is going to be a positive turn of alpha j degrees or radians, whatever you like, about or around the x-axis. Okay, so which will make something like, okay, initially if this was the direction of the z-axis, then the final direction would be in something like here. Okay, and with these four motions we can reach from this origin and this orientation, the one from coordinate frame j minus 1, to this origin and this direction, which are corresponding to joint j plus 1. Okay, so two things have to be highlighted. Joints are either rotary or translational, okay, or prismatic, if you allow me. Okay, what is a rotary joint? A rotary joint is a joint where this parameter theta is not fixed. It changes with the rotation of the joint. On the other hand, a linear or a prismatic joint is the one where this parameter moves and it doesn't remain fixed a long time. Okay, normally one of the two parameters changes with time, not the two of them. Okay, just one. And as you can see clearly, either in both cases, no matter if it is a rotary or a prismatic joint, the axis of the rotation or the displacement is always the z-axis, axis of the j-1 joint. Okay, so these two parameters can be variable, but in practice only one of them is variable at a time. The other is fixed. It need not be zero. It could be something different than zero, but it's not fixed. Okay, The other two parameters, aj and alpha j, are fixed parameters, are constants. They cannot change with time. So in a way, the relative position of the z-axis of both rotations remains fixed with time. There's another interesting point, okay? If I am talking of geometrical displacement or transformations for going from j minus 1 to from j to j plus 1, then in general I am referring one reference frame to another reference frame, okay? And the point, this is from joint j and this is from joint j plus 1. And the point is that in mathematics, two reference frames in 3D need 6 geometrical operations or 6 degrees of freedom to reach from one to the other. So why are we using 4 instead of 6? Well, it is a subtle thing but very intelligent. The dynamic hardware parameters are the minimum number of parameters needed for placing in space one joint with respect to the other. But one joint is not exactly the same as a coordinate frame, because if we, I'm going to draw in red now, if we observe these 2 points, okay, the origin of the coordinate frame of joint J and the origin of the coordinate frame of joint J plus 1 are not fixed. I mean, the robot would be the same, would behave exactly the same if we change the origin of the coordinate frames. So we have no constraint in the position of the coordinate frame of a joint J and joint J plus 1. And this reduces the number of degrees of freedom to reach from one joint to the next, okay? And the other thing is that, okay, the dj coordinate and the theta j coordinate can change with time, but the zero, I mean the original value of theta and d are arbitrary. I mean, I can set up the zero in such a way that after rotating, the x direction points exactly a direction that intersects this axis. And this property reduces again 1 degree of freedom, and that is why we need only 4 dynamic hardware parameters to reach from joint J to joint J plus 1. Okay, so it's subtle, so I need you to make a reflection on this. I need you to be able to describe step by step the displacement and rotations of the dynamic hardware parameters, and once you do that, you will very clearly understand the logic. Okay, so where do we want to go by describing the dynamic hardware parameters? Well, as you have probably imagined, we want to be able to compute the homogeneous transform matrix that changes coordinates from coordinate frame J to coordinate frame J minus 1, okay? Or from joint J plus 1 to joint J, right? This is very important. I will not stop saying that. We need a coordinate frame change homogeneous transform matrix, right? And if we know the geometrical operations that go from this coordinate frame to this coordinate frame, then we will be able to compute that matrix. How? Okay, here's the expression. The homogeneous transform matrix that transforms from J to J minus 1 is the product of the matrices corresponding to the sequence of operations that go from J minus 1 to J, okay? So here we have to be careful and remember very well the first lesson, okay? Where we introduce this idea, transforming from J to J minus 1 means using geometrical operations from J minus 1 to J, okay? these two ideas are opposite in some sense. Okay, and the geometrical operations, as we all know, is first a rotation of theta degrees around the z-axis, so that's why we write TRZ. Then to the resulting coordinate frame, we apply a linear displacement of dj along the resulting z-axis. Then to the resulting coordinate frame, we apply a linear displacement of aj, and then finally to the resulting coordinate frame, we apply a rotation alpha around the x-axis. And the product of these four homogeneous transform matrix will result in this matrix called j-1 aj, transforming from j to j-1. And this is, well, there's some complexity in reading this. There are sinuses and cosinuses of theta, alpha, and also there's this distance dj, and there's this distance alpha j. Okay, as any homogeneous transform matrix, it has final row as 0, 0, 0, 1. Okay, and this submatrix that we observe here, sorry, I don't like this color, this submatrix, as you can imagine, is a rotation matrix that has the orthonormal property. Okay, and this actually was just a reminder because it's something that we saw the other day, but it's good to have this in this video already. So how about have this in robotics toolbox? Okay, so the first idea in robotics toolbox is that a robot is a chain of links. Okay, a chain of links. This is link 0, this is link 1, this is link 2, all right? And there are coordinate frames associated to each of those links, right? Okay, so there's a coordinate frame here, there's a coordinate frame here. The robotics toolbox, for the moment, for kinematics, doesn't consider anything more than the coordinate frames. Okay, it doesn't care about whether these parts of the robot are bigger or closer, or are heavier, or are rounded, or are triangle shaped, or whatever. Okay, it only cares about coordinate frames, right? So we are going to create a model of the robot, of a simple robot in robotics toolbox. And in order to do that, we are going to use the link function, okay? And in order to define a link, okay, a link is this, actually. So in order to define a model of a link, I will define the geometrical relation of the two joints at the end of the link. Okay, so how do I define the geometrical relation? By defining its Dinavit-Hartenberg parameters, right? So the function that creates a model of a link, it should receive the four Dinavit-Hartenberg parameters with theta, d, alpha, a, and alpha. Okay, and it also receives an extra parameters that just specifies whether it is a revolute or rotary revolute. It's okay, joint, or sigma equals 1 for a prismatic joint. I think it's easier to understand this idea. But the best way of learning how common is used in MATLAB is just writing an example. So we write L equals link, this is the function link, parenthesis, okay, and the function link will receive these parameters according to the previous table inside vector brackets, okay, so it is receiving a 5D vector containing, as you have already seen, theta j, dA, aj alpha j, and that's why you see the pi over 2 parameter here, which would clearly suggest that it is radians what it uses, and the 0 indicated that it's a matter of we are talking about a revolute joint. Okay, so if we click on enter without any semicolon here, then MATLAB will display the answer to this operation, and it confirms that a new joint has been created by defining these parameters: theta equals q, d equals 0.1, alpha equals 0.2, alpha equals a equals 0.2, alpha equals 1.57, and then this indicating that it is a revolute joint, and here STDDH, standard dynamic hardware. Just one extra comment. We said theta j equals 0. In fact, theta is a variable, okay? It changes with time, so it's not fixed, it's not a fixed parameter, but we could have given it an initial value, okay? Because in this construction, normally there is a, okay, let's look at here, exactly at here. So after applying the dynamic Hartomer parameter, we have a coordinate frame of a coordinate frame J, and if we want the 0 of the coordinate to be exactly in that orientation, that's okay. But sometimes we need to define the 0 of the coordinate, of the theta coordinate of this coordinate frame to another position or pose of the coordinate frame. In that case, we should define something like an initial value of theta, such that the 0 should start in the proper position or orientation, right? So that's why the link function allows us to give here an initial value of theta j, right? So for me, it is also important that you try these, okay? So, right. So L.A, well, this is a syntax that we have to start getting accustomed to. Is that the variable L is a variable, okay? Because it is created the moment we assign it to the result of the link function, but is something bigger than a variable, okay? L is an object, okay? But an object is something that should not confuse you and should not make you scared. You have used a lot of objects in MATLAB. An object is a variable because it has values like a vector or a matrix. So it contains values, inside, is like for storing values, and it contains also behaviors, okay? Or better than behaviors, methods. Okay, what are methods? Methods are things that I can do with those values that are inside the object, okay? So, for example, a matrix M has values, and I can access those values by writing this. But there are operations that I can do with a matrix, which are like computing its determinant. Well, in object-oriented MATLAB, sometimes we could write this in a different way, because as the method determinant is something that in a way belongs to the matrix or is specific to the matrix, sometimes we can write this syntax: the name of the variable and then the name of the method followed by parentheses. Okay, so this is another way of stating that I'm going to compute the determinant applied to the values of matrix M. Okay, so well, let me just point out that this is some example that is shown here for clarity, but matrices don't accept this syntax. But link objects do accept this syntax, and this is what I'm trying to highlight here. So L is an object, and doing an operation in that object can be done by using L dot and the name of a function, following by parentheses and possibly by parameters. And this is the example. A, capital A, is a function that is included in the object L. And 0.5 is the parameter of that function. Okay, what does this mean? Well, this just computes the homogeneous transform matrix that relates the two coordinate frames that are at the edges of link L. Okay, so this homogeneous transform matrix that would change from the coordinate frame of the right, I'm saying right just for clarity, okay, the J coordinate frame to coordinate J minus 1, the two edges of the link, okay? And of course, this matrix needs a parameter. This is exactly the value of theta J for which the matrix A is going to be computed, okay? Because as theta is variable, A will not specify until we choose the value of theta, right? So this is a function that computes the transformation matrix for joint L, okay? So please try this and and just try to check by yourself how they behave. And after that, before making the next step in robotics toolbox, we are going to explain a concept which is very natural now, which is the forward kinematics, okay? And it is the expression that gives the position, well, okay, to be precise, it is the pose, but sometimes it is easier for you to talk about positions, okay? So the position of the end of the robot, the end effector, the hand of the robot, the extreme part of the robot, okay, right? In world coordinates. So it just tells us what is the location of this coordinate frame in red with respect to this coordinate frame, which is the world, okay? This is the end coordinate frame, and we need to refer it to the world. We need to have the homogeneous transform matrix that relates both coordinate frames. Now, with the risk of being insistent, I will go back to the previous uses of homogeneous transform matrices. Do you remember them? Okay, so one of the uses of the homogeneous transform matrices was just changing coordinates from one coordinate frame to the previous. But this is not the only. Remember that the use of these matrices was also just to specify relative positions or relative poses of coordinate frames, right? And this is what we are looking for. So we are looking for specifying the relative poses of the hand of the robot with respect to the base. Okay, and as you can all imagine, if the relative position of one coordinate frame J j minus 1 with respect to j is a function of theta j dj aj alpha j, then the relative position of the coordinate frame of the end of the robot with respect to the base is going to be a function of all these values in all the joints of the robot, okay? So if I change just one single value of theta j of dj in any one single joint of the robot, then the total matrix that goes from here to here changes, okay? So in practice, what I'm saying is that I'm looking for an expression, a function that gives us the pose of the end effector as a function of all the values of theta and d at a given time. And these values of theta and d are going to be called from now on a vector of generalized coordinates, okay? That in the case of a Revolute robot is just the set of values of theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. Okay? Thinking about robots of 6 degrees of freedom, right? So Q is the vector of generalized coordinates, which is the set of variables that change with time for each of the joints, okay? Put all together in a vector. If it is a robot made only of Revolute joints, then it's going to be the set of theta values from theta 1 to theta 6, right? And, okay, this function that depends on Q, that is, depends on all the theta, gives us a homogeneous transform matrix, right? So, right, that describes the position of the end of the robot with respect to the universe. That's we have already specified that. Okay, and now if we look at this very dirty image, sorry about that, but if we look back at this, we can compute the relative position of the red coordinate frame with respect to the blue by relating first the coordinate frame of the final joint with respect to the previous one, and this would be related with respect to the previous, and this would be related with respect to the previous. So there's a chain of coordinate changes from here to here, from here to here, from here to here, and each coordinate change implies the multiplication of one matrix of this type. That is, the matrix that moves from one joint to the previous joint. So if I have a set of coordinates in the end effector frame, then by multiplying it by this matrix, I would change those coordinates to the previous coordinate frame. So initially, xn would be in the end effector frame. If I multiply by this, what would I get? I would get the same point or vector in the previous coordinate frame. So then what should I do next? I should multiply it by an minus 1 and an minus 2. And then I will get the same vector in coordinates a minus 2. And that's how it goes to the left until, okay, we keep on multiplying to the left until we reach this matrix, which would transform the vector in coordinates of the universe, right? So this multiplication in series would give us the total homogeneous transform matrix that transforms coordinates with respect to the end effector to coordinates with respect to the universe, right? And this is what we call G sub E, and this is the main expression that we are searching for in this slide, okay? And this main expression appears here. And this expression is called the forward kinematics. Now we are going to work with a model of a real robot. Okay, why not? Right. So this robot is a planar robot, right? A planar robot is a robot where all the motions remain in the same XY plane. There's no Z motion. There could be physical items in the Z directions, but all the motions happen in a plane. Okay, this is a nice example for studying the basic kinematics of a robot. And as we can see here, okay, so there is a 0 coordinate frame here, which is the universe. Then corresponding to the first joint, there's a 1 coordinate frame corresponding to the second joint, and there's a 3rd coordinate frame, okay? Right. In here. It's not corresponding to a joint, it's associated to the end effector. Right, so how we do specify the motions of the coordinate frame, okay? Well, one motion is just, okay, sorry, this should be, it's the second, but it's called 1. So this is one link, okay, and this gives us a matrix A10, okay, and this is another link, and it should give us the matrix A21. All right. Okay. It is clear that the coordinate change from 2 to 0 is the product, remember, from right to left. Okay. And it is clear that A20 is a function at any time of the values of the coordinates, generalized coordinates Q1 and Q2. Okay, those are the generalities. Let's just be precise. Let's write the dynamic Hartman parameters of these simple robot. Okay, we will deal with the robot as if it were in 3D, right? For that, we will just have to assume that the Z vector is at all times coming out of the plane, the image plane. Okay. And first of all, we have to specify the joint angle. And what happens with the joint angle is that it is variable because it is a revolute joint. Okay, so it's Q1 and Q2 at all times. So it's not specified, but we will give it an initial value of 0. Right. Then the link offset. The link offset is the link displacement along the z-axis. Okay, but as everything remains in the same plane of the image, there is no displacement along z. So this is right 0. This is very simple. Then we should specify the distance that has to be performed along the axis of along the x-axis of the coordinate frame after rotating it theta to reach from exactly from here to here. Okay, so remember, starting from coordinate frame 0, we made first a rotation theta j, then a displacement dj, which is 0. So we have the x coordinate frame in here, and then the displacement along this coordinate frame is what we call aj. In this case, it is called a1, and it is here. We give it a value of 1. It could be 2, 3. It's just the length of the arm of the robot. Okay, and finally, you have to perform a twist of alpha degrees along the resulting x-axis. Okay, this is the resulting x-axis, and of course there is no twist about it. Okay, this is 0, otherwise it would stop being a planar robot, right? And we have to specify whether each joint is revolute or is prismatic. And that's why we set a 0 in here, right? Okay, so using this for the 5D9 with Harton parameters, so excuse me, there is a 0 missing here. Okay, so by setting this, we are specifying L of 1 is going to be the first link. L of 2 is going to be the second link. Why L1 and why L2? Okay, I could say I could just write L1 equals the first link and L2 equals the second link. Then it's nice, I would have a couple of variables called L1 and L2. But for the next step, I have an interest of having both variables inside a vector, okay? So that's why we are going to create a vector of links whose first element is L of 1 and the second element is L of 2. You will see very quickly why in the following. If I make these two assignments and I write L just in the prompt line of MATLAB, then MATLAB will give us as a vector the set of the Navitt-Hartenberg parameters of these two links that we have just set. And the nice step is the following. We are going to create a robot model by calling the serial link function, right? And the serial link function receives a vector of links, and that's the idea of combining them two together inside a vector. Receives the L vector that we have just created with two links. It receives just a name, and a name to be depicted in the picture, okay? The first to be made reference inside programs, and this to be plotted in pictures. Right, so L is an array of links. In this case, it has two links, but it can have much more, as many as we need to define our robots. Okay, the forward kinematics. Now, remember, the forward kinematics was the computation of the matrix that transforms from the end effector to the universe as a function of the present value of each of the generalized coordinates, right? Well, okay, just write toLink, okay, in MATLAB, which is, remember, the result of the call to serial link to the serial link function, and MATLAB will give us a summary of how it is, how is the data of this toLink function, okay? This is what is giving us, and apart from the Navitt-Hartenberg parameters of each of the joints, we have also the gravity vector, we have also the base vector, and we have also the tool vector. Why? Because, okay, up to now, we have defined everything with respect to this coordinate frame that we call 0. But in practice, MATLAB allows us to have another coordinate frame in game, which is a 0 coordinate frame which is outside the robot, which is not the base of the robot. So up to now, we have made these two coordinate frames the same. But in order to make realistic applications, we must think of the possibility of the robot being placed somewhere else than in the origin of the universe. For example, if you have two robots, then you cannot make the origin of the universe the base of the two of them. So at least one of them should be at a different location than the universe. So MATLAB allows us to separate the universe coordinate frame from the base coordinate frame. And when this happens, we should define the relative pose of B with respect to O. And this is what appears here as the base homogeneous transform matrix. We are going to further work in that, right? Okay, and the tool allows us to, well, once we reach here, there might be another coordinate frame, sorry, I'm going to make zoom. There might be another coordinate frame here that is better aligned with the tool. So for some specific operations like drilling, machining, and things like that, you might prefer to have a new coordinate frame here, which is not the final coordinate frame of the kinematic chain, right? And this is why you would use the tool coordinate frame. We will not use this actually. This is just going very far and it's not really needed for understanding. Well, before stopping, we will make a quick plot of the robot. Okay, so if I write tooling, which is our new sorry, okay, there's this underscore. There's some confusion here. Sorry, there should be an underscore here. So in order to plot it, to visualize it in 3D and understand what is happening, we can call the function plot, which is part of the object tooling, and using parentheses, we should specify the value of the theta coordinate for all of the two coordinates of the robot. So if we set them to 0, 0, then we will have this image. That it might sound strange at first sight, but if we look at it from the top, we will recover the initial image of our robot. Sorry, I skipped some slide here. Yeah, okay, this initial image is exactly the one that we are obtaining in 3D. The problem is that when it is in 3D, we will see this from the upper perspective. But when we look at it from the right, then we are not given the upper perspective. But it's clear, no? This is the Z direction, okay? And the Z direction is the one that was not seen before, right? So X, this is Y, this is positive Y, and this is Z, right? Okay, and this is what we get if we set the coordinates of the robot as pi over 4 and minus pi over 4 as appears in this second function call. Okay, I'll stop the video right in there. Sorry.